Have you ever imagined a computer that could solve problems currently considered impossible? Problems that even the most advanced supercomputers in the world would take billions of years to complete. Imagine a technology that could revolutionize medicine, create new materials with never-before-seen properties, and even change the way we understand the universe. It sounds like science fiction, doesn't it? But this is the promise of a revolution currently underway in the world of computing. The quantum computer revolution. Get ready, because what you're about to hear will change the way you see the future of technology. To truly appreciate the quantum leap we're about to discuss, we first need to understand the landscape we're currently in. The world of classical computing. Think of it as a long journey that began with a simple invention, the switch. In the world of computing, that switch is called a transistor. It's these tiny billions of transistors that form the foundation of every digital device we use today. From the smartphone in your hand to the supercomputers that fill entire rooms. Classical computers operate on a binary principle, which we know as the bit. Every bit can only have one of two states, a 0 or a 1. There is no in-between, it's a clear, absolute choice. The numbers, text, images, videos, and even sounds we enjoy on screen are merely representations of these billions of bits being arranged and manipulated at incredible speeds. This speed has been constantly increasing, driven by an iconic prediction, Moore's Law. In 1965, Intel co-founder Gordon Moore observed that the number of transistors on a chip would double approximately every 2 years. For over half a century, this prediction held true, propelling us into an era where computing devices became smaller, cheaper, and faster. However, beneath this incredible acceleration lies a fundamental, unavoidable limitation. This isn't just about how small we can make transistors. It's about the very nature of how computing works. The processor in your computer, no matter how fast, works sequentially. It performs tasks one after another. To solve a problem, it has to try every possibility, check every scenario one by one. Even at speeds of trillions of operations per second, this approach has a clear bottleneck. Let's take a simple example, solving a puzzle. Imagine you have a box of thousands of keys and you have to find the right key to open a lock. A classical computer would try every single key one at a time until it finds the correct one. It's a method that is guaranteed to work, but it becomes incredibly time-consuming if the number of keys is vast. In the real world, many problems are far more complex than a simple lock and key. These problems have a number of possibilities that isn't just large, it grows exponentially. This means every time you add one variable, the number of possible solutions skyrockets, much faster than we can increase our computing speed. This is what's called a combinatorial explosion. Problems like this are simply out of reach for classical computers. For instance, consider molecular simulation. In drug discovery, scientists need to understand how a drug molecule interacts with a protein molecule in the body. Each molecule consists of atoms that interact in complex ways based on the rules of quantum physics. Using a classical computer, simulating even a relatively simple molecule with, say, 100 atoms is a nearly impossible task. The number of possible atomic configurations is so immense that even the fastest supercomputers would need billions of years to explore all the possible interactions. Another example is optimization. A large logistics company needs to find the most efficient delivery routes for thousands of packages to thousands of different locations. Every package and every location is a variable. Finding the absolute best route to save time and fuel, while accounting for changing traffic conditions, is an exponential optimization problem. Even with all the clever algorithms available, a classical computer can only provide a good enough approximation, not the truly optimal solution. This limitation also extends to cryptography. Modern encryption algorithms like RSA rely on the fact that factoring a very large number into its prime factors is an impossible task for a classical computer to do in a reasonable amount of time. The security of all our digital data, from banking transactions to private messages, depends on this mathematical difficulty. But classical computers are fundamentally not designed to solve this type of problem quickly, so we arrive at a dilemma. We have incredible computing technology that has transformed our lives in every way, yet we're hitting an invisible wall, a wall made of mathematical complexity and fundamental physics. We've squeezed every last ounce of power from the zeros and ones architecture, shrinking transistors down to the atomic level. Moore's Law, which has been our guiding light, is now faltering, and we're realizing that simply making processors faster won't be enough. This is why scientists started looking elsewhere. They looked to another, stranger and more mysterious world. The world of quantum physics. A world where particles don't just choose 0 or 1, but can be both at the same time. A world that defies our common sense, but one that may hold the key to solving the problems that have been impossible until now. This is the beginning of the revolution to come. If the world of classical computing is logical and predictable, then the world of quantum mechanics is its opposite: strange, counterintuitive, and full of mystery. It's a world that can't be understood through analogies from everyday life. It operates on an infinitesimally small scale, where the rules of physics as we know them no longer apply. It is here at the level of atoms and subatomic particles that the key to the future of computing lies. The birth of quantum concepts began in the early 20th century, when physicists discovered that tiny particles like electrons and photons didn't always behave like predictable solid objects. Instead, they exhibited both wave and particle characteristics at the same time, a concept known as wave-particle duality. But the two most fundamental and relevant principles for quantum computing are superposition and entanglement. Without a deep understanding of these two concepts, we cannot move forward in comprehending the power of quantum computing. Superposition. Let's think for a moment. In the classical world, a light switch can only be in one of two states, on or off. A bit in your computer is a direct analogy. It can only be a 0 or a 1. But in the quantum world, a particle, like a spinning electron, can be in a state of superposition. This means it is not entirely on or off, not entirely a 0 or a 1, but rather in a combination of both states simultaneously. Imagine a coin flipped into the air. As long as the coin is spinning, we can't definitively call it heads or tails. It's a mixture of both. Only when the coin lands does its state collapse into one of the two possibilities, heads or tails. A qubit or a quantum bit behaves exactly like this. As long as it's not measured, it exists in a superposition of 0 and 1. It carries the potential to be both. The moment we measure it, it's forced to choose one state. This ability to be in superposition is a source of immense power. If you have one qubit, it can be both 0 and 1 at the same time. If you have two qubits, it can represent 4 possibilities simultaneously: 0, 0, 1, 10, and 11. If you have 10 qubits, they can hold 10,024 possibilities at once. This number grows exponentially. With just 50 qubits, you can represent more information than the total number of bits in all the supercomputers in the world today. This is what allows a quantum computer to perform incredibly complex calculations by exploring many solution paths in parallel, not one by one like a classical computer. Entanglement, quantum entanglement. If superposition sounds strange, get ready, because entanglement is an even more mind-bending concept. Entanglement occurs when two or more quantum particles become linked or entangled in such a way that their quantum states are interdependent, no matter how far apart they are. Imagine a pair of gloves. If you have a pair of gloves and send one to the other side of the galaxy, you would know with certainty that the remaining glove is the left one. By looking at one glove, you instantly know the state of its pair. Entanglement works like this, but in a much deeper and stranger way. When two qubits are entangled, if you change the state of one qubit, the state of the other qubit will change instantaneously, even if they're separated by a vast distance. This connection is so strong that Albert Einstein, who found it impossible, called it spooky action at a distance. In the context of quantum computing, entanglement allows scientists to build a highly coordinated network of qubits. This enables a quantum computer to perform complex operations on many qubits simultaneously, creating connections that are impossible to achieve with classical bits. Entanglement allows for complex interactions between qubits, optimizing the computational process that cannot be broken down into individual calculations. Simply put, superposition gives a quantum computer the raw power to process many possibilities at once, while entanglement provides the connectivity needed to coordinate and manipulate that information on a large scale. These two concepts are the fundamental pillars that distinguish quantum computing from everything we have ever seen before. Without this bizarre and amazing quantum physics, the dream of solving impossible problems would forever remain science fiction. But by harnessing these principles, scientists now have a blueprint for building machines that will change the world. If the previous section was about theoretical concepts, now we're going to step inside the heart of the machine itself. Let's break down how the strange principles of quantum physics are translated into a tangible computing device. The core of it all is the qubit, or quantum bit. In a classical computer, as we've discussed, a bit is a switch that can only be on 1 or off 0. It's simple and straightforward. In a quantum computer, however, the qubit is far more complex. A qubit harnesses the principle of superposition, which means it can be a 0, a 1, or a simultaneous combination of both. This is the fundamental difference that changes everything. Imagine a qubit as a spinning ball. The ball isn't just spinning on its north pole, representing a 1, or its south pole, representing a 0, but can spin at any point on its surface. The ball's position on the surface determines its probability of being a 0 or a 1 when measured. As long as it isn't measured, it exists in all of those possible positions at the same time. This is a capability a classical bit simply doesn't have. How are qubits physically created? There are several ways, and this is one of the hottest areas of research. One of the most common methods uses superconducting circuits. These circuits are cooled to incredibly low temperatures, approaching absolute zero, so that electricity can flow without resistance. In these extreme conditions, the circuit exhibits quantum properties, and the oscillations of current within it can be manipulated to act as a qubit. Other methods use trapped ions in an electromagnetic field or even leverage photons, particles of light. Regardless of the method used, the goal is the same: to create a fragile, isolated, and controllable system that can maintain its quantum properties for as long as possible. The computing process in these machines is also very different. Instead of a series of arithmetic and logical operations on bits, a quantum computer performs operations called quantum gates on qubits. These quantum gates are subtle manipulations that change the superposition and entanglement states of the qubits. A quantum gate doesn't just flip a 0 to a 1 like a classical logic gate, but can also rotate the qubit ball to another position on its surface, changing its probabilities. The most famous example of a quantum gate is the Hadamard gate, which acts like magic. It takes a qubit that is in a 0 state and puts it into a perfect superposition of both 0 and 1. This is the first step in enabling the qubit to explore multiple solution paths simultaneously. Then there are quantum gates that leverage entanglement. Gates like the C-NOT, controlled NOT gate, can link two qubits together. This gate will flip the state of the second qubit only if the first qubit is in a certain state. By applying such gates to a network of entangled qubits, a quantum computer can perform incredibly complex calculations that leverage the correlations between qubits. It's the computing power that results from this combination of superposition and entanglement that creates a combinatorial explosion in quantum space, allowing for the solution of problems that are impossible for a classical computer. But behind all this magic, we have to remember one thing. Every time we want an answer, we have to measure the qubits. When we measure them, their superposition state collapses into either a 0 or a 1, and what we get is a single answer, the result of all the possibilities that have been processed simultaneously. It's as if we ask the spinning ball to stop and show us which side is facing up. This is why programming a quantum computer is so different. A quantum programmer doesn't just write instructions, but intelligently designs an algorithm that manipulates the probabilities so that the probability of getting the correct answer is much higher than any other. So, even though we only get one answer, we know that this answer is the result of a vastly more efficient search through the entire solution space. Technically, today's quantum computers are still in their early stages. We have what are called NISQ, noisy intermediate scale quantum devices, which are devices with a limited number of qubits that are prone to errors. One of the biggest challenges is decoherence, which is when the quantum state of the qubits is disturbed by tiny interactions with the environment, such as vibrations or temperature changes, causing them to lose their quantum properties. This is why modern quantum computers have to be isolated from their environment in the most extreme way, often being housed inside specialized refrigerators that cool them down to temperatures colder than outer space. Despite these challenges, the way a quantum computer works is a testament to human ingenuity, harnessing the strangest properties of physics to create a tool that can change the future. These machines are not just faster versions of our computers. They are a completely new kind of computing, with a potential we've only just begun to understand. Now that we understand how a quantum computer works at a fundamental level, let's talk about why it all matters. If classical computers brought us into the information age, then quantum computing promises a leap into an entirely new era. Its potential isn't just about making devices faster, it's about solving problems that have been impossible until now, unlocking doors to discoveries that will transform civilization. Let's look at some of the most promising applications this technology will enable. 1. Drug discovery and new material design. Behind every disease and every material innovation lies a complex interaction at the molecular level. Classical computers struggle to simulate these interactions because the number of possibilities is astronomical. A drug molecule interacting with a body's protein could have trillions of different configurations. A quantum computer, with its ability to process multiple possibilities in parallel thanks to superposition, can mimic the behavior of molecules and atoms with much higher accuracy. This will accelerate the discovery of new drugs, allowing us to design molecules that specifically target cancer cells or viruses, and create materials with never-before-seen properties, like superconductors that work at room temperature or vastly more efficient batteries. 2. Artificial intelligence and machine learning. Today's artificial intelligence, AI, relies on incredibly complex algorithms and massive datasets, but there are limits. Quantum computers can process data in a fundamentally different format, allowing machine learning algorithms to find patterns in data that are too complex for classical computers. This could lead to more sophisticated AI models, more accurate pattern recognition in medical imaging, and the ability to process data on an unprecedented scale. One example is quantum machine learning, a new field focused on developing machine learning algorithms that harness quantum principles to solve the toughest problems. 3. Optimization and logistics. Many real-world problems, from determining the most efficient delivery routes to managing investment portfolios, are optimization problems. These problems have an infinite number of solutions. Classical computers use heuristic approaches to find a good enough solution but can never guarantee the best one. A quantum computer can explore a vastly larger solution space simultaneously, allowing companies to find the most efficient shipping routes, optimize airline scheduling, or manage energy grids in a way that saves billions of dollars and reduces emissions. This is the holy grail of optimization. 4. Cybersecurity and cryptography. While quantum computers could pose a threat to current security systems, they also offer a solution. Modern encryption algorithms rely on the difficulty that classical computers have in solving prime factorization problems. Quantum algorithms, such as Shor's algorithm, have the potential to break this encryption in seconds. This poses a major challenge to global data security. However, scientists are also developing post-quantum cryptography, new algorithms designed to be resistant to attacks from quantum computers. Furthermore, the field of quantum key distribution offers a fundamentally secure way to exchange encryption keys. The quantum computer is essentially a double-edged sword in the world of cybersecurity, and we must be prepared for both sides of that blade. The potential of quantum computing is so vast and profound, touching almost every aspect of modern life. From predicting the behavior of financial markets to solving the biggest puzzles in particle physics, this technology will be a catalyst for unimaginable discoveries and innovations. We stand on the verge of a truly new era, one where computing is no longer just about speed, but about unlocking entirely new dimensions of understanding and possibility. While the potential of quantum computing is thrilling, we have to be realistic. The technology is still in its infancy and faces significant hurdles that must be overcome before we can see it in widespread use. Building and operating a quantum computer is one of the toughest engineering challenges humanity has ever faced. 1. Fragility and decoherence. The single biggest challenge facing quantum computers is decoherence. Remember how fragile a qubit's superposition state is? It's extremely delicate. The slightest interaction from the environment, such as vibrations, electromagnetic radiation, or even heat, can destroy the qubit's quantum state, causing it to collapse before the calculation is complete. This is the equivalent of a calculator randomly giving you the wrong answer. To combat decoherence, modern quantum computers have to be isolated from their environment in the most extreme way. This involves cooling qubits to temperatures approaching absolute zero, 459.667 degree Barn or 0 Kelvin, which is colder than deep space, and shielding them with vacuum chambers and magnetic fields. This massive and complex infrastructure is why today's quantum computers are so large. 2. Scalability and quantum error correction. Another major issue is scalability. While we've managed to build computers with dozens or even hundreds of qubits, building thousands or millions of them that function coherently is a much greater challenge. For a quantum computer to solve practical problems, it needs a large number of qubits that not only interact well, but can also withstand errors. To address this, scientists are developing methods for quantum error correction. In classical computing, if a bit flips, a 0 becomes a 1, we can easily correct it. But in quantum computing, an error can be a tiny change in a qubit's probability. Quantum error correction is a very complex science that requires many physical qubits to secure a single, error-free logical qubit. This means that to make one truly stable qubit, we may need hundreds or even thousands of physical qubits. 3. Quantum algorithm development. Even with the machines, we need the language to speak to them. Currently, there are only a handful of algorithms that are exponentially faster on a quantum computer than on a classical one. These algorithms, such as Shor's algorithm for factorization and Grover's algorithm for database searching, demonstrate the quantum potential, but we still need many more. Developing new algorithms that fully leverage quantum power is an intense area of research. The future of development, the hybrid era, and the quantum internet. The future isn't bleak, though. Scientists and engineers worldwide are making incredible progress. Quantum computers won't replace classical computers. Instead, they will work together. We will likely enter an era of hybrid computing, where classical computers handle mundane tasks while a quantum computer is accessed via the cloud to solve the most difficult problems. Furthermore, the emergence of a quantum internet promises a revolution in communication. Using the principle of entanglement, a quantum internet could create a network that is inherently secure, where data cannot be intercepted. It would be the most secure communication network ever created. In short, the journey to a powerful, practical quantum computer is a long one. It's a road filled with fundamental physics, engineering, and computer science challenges. But with every breakthrough, we get closer to realizing the promise of these machines that will shape the future. The age of quantum computing won't arrive overnight, but every day we're building the pieces of the puzzle that will one day change the world. Now let's bring it all together. Imagine a future where deadly diseases are cured with drugs designed for an individual's unique genetic makeup, where superconductors revolutionize energy transmission, and where unparalleled artificial intelligence algorithms solve our most complex global problems. This is the vision that the quantum computing revolution is driving. From the strange principles of quantum mechanics to the transformative potential of its applications, this technology promises an exponential leap in our computational capabilities. While the challenges are significant, the spirit of discovery and innovation in this field is incredibly strong. We are at the very beginning of a new era in computing, an era where the boundaries of what is possible will be continuously pushed and redefined. The quantum computing revolution is no longer a theoretical concept. It's a rapidly evolving force, poised to shape our future in ways more profound than we can currently imagine. Are you ready to keep up with the cutting-edge technological revolution that's changing the world? Do you want to dive deeper into the science and innovation shaping our future? Don't miss out on more mind-bending knowledge. Hit that subscribe button now and turn on notifications so you don't miss our next videos, where we'll continue to demystify the incredible innovations that are shaping our future. Let's keep learning and exploring the frontiers of knowledge together.